Swayam Prabha. Digital India. Educated India.
One three conjugate S23 equal to 0. Now let us analyze these two sets of equations. Let us consider, say, this equation. This implies that either of the magnitude of S13 or the magnitude of S23 is 0. Let us assume that S13 magnitude is equal to 0. Okay, or both could also be 0. Both the magnitudes of S13 and S23 could also be 0. That's also good. But let us for a moment assume that only S13 magnitude is 0. So if this is the case, then if we substitute this equation in this equation, we get S23 magnitude is equal to 1, right? And from this equation, if we substitute this value here, then we get S12 magnitude equal to 1. Fine. Okay, now let us consider this equation. So here either of so here again this satisfies that S12 conjugate S13 multiplied by S13 is equal to 0, because we have taken because this equation is true. So if S13 magnitude is equal to 0, then this expression will also be equal to 0. Let us see this equation. Now here one of the two, that is either S12 magnitude or either S12 magnitude or S23 magnitude, has to be equal to 0 in order for this product to be 0. But we have just seen that S23 and S12 both are non-zero. So there is a conflict. So this equation doesn't have a solution. In fact, if we consider only, here we have assumed all three ports to be matched, and that's why we get S11 equal to S22 equal to S33 equal to 0. If we had taken, say, the condition S11 is equal to S22 equal to 0 and S33 is not equal to 0, then also we would see that we get unsolvable equations. However, if we have only one port match, that is, say, S11 equal to 0 but S22 not equal to 0 and S33 not equal to 0, then we do have a solution. So in other words, we can have, for a 3-port network, first of all, we cannot achieve reciprocity losslessness and matching at all ports. These three simultaneously is not possible for 3-port networks. We can achieve one by one, or we can achieve two of the conditions. Okay, so for example, we can have, say, we have this, let's write down this property: lossless reciprocal matched at all ports. Okay, A three-port network which is lossless and reciprocal but not matched at all ports is called a T. A three-port network, so for a T it is lossless and reciprocal. A three-port network which is lossless and matched but not reciprocal is called a circulator. A three-port network which is reciprocal and matched at all ports but is not lossless is called a power divider. Okay, so see, for a circulator and power divider, we can achieve matched at all ports, this property. For a T, we cannot achieve matched at all ports, but we can achieve losslessness and reciprocity. But we can achieve matched at one port. Okay, maybe not. So a T can not be matched at all ports, but it can be matched at one port because of this derivation. You can, I leave it to you to prove that if this condition is satisfied, that is only one port is matched, then the unitary condition, this one, has a solution. Okay. So now what we will do is we'll one by one study these circuits. So let us start with the T. There are first of all two types of T's. Okay. Now an E-plane T is has a diagram like this. I'll try to draw as best as I can. This is an E-plane T. An H-plane T has the same shape, but the narrower and broader edges are reversed. So let me show it, draw it. these blue lines represent the magnetic field and the red lines represent the electric field. Of course, there are various modes present. This is one of the modes. This is the actual shape for various modes may be different, but the general sense is that for the E-plane T, this is the general sense is that for the E-plane T, the electric fields are between the surfaces as shown, whereas for the H-plane T, the electric field is perpendicular to the plane of the T as shown. So it is coming out like this. These are coming out of the surface of the T. And the magnetic fields are concentric around the electric field. Similarly, for the E-plane T, the magnetic field might be something like this, something like this. Okay. So as you can see, the E-plane T and the H-plane T have the same shape, but the E-plane T has the broader edge here, whereas the H-plane T has the broader edge here. And because of this, the direction of the electric and magnetic fields are also different. One notable difference in the E-plane T is that note the direction of the electric field at this point and at this point. They are opposite. Now what we can do is we can label the various terminals. Suppose I call this end as port 1, this as port 2, and this as port 3. Similarly, for the H-plane T, I label this as port 1, this as port 2, and this as port 3. Now, these ports are points through which power can enter or exit the T. Okay. So now because of the difference in the direction of the electric field for this E-plane T between the ports 1 and 3, we can write just by observation that S12 will be equal to minus S32. This is a reciprocal device. So S12, for example, will be equal to S21, S23 will be equal to S32, and S13 will be equal to S31. Now, in the case of the H-plane T, you see that the direction of the electric field remains the same in ports 1 and 3. Therefore, S12 is equal to S32, and the other properties will also be valid. For example, S12 will be equal to S21, S23 is equal to S32, and S13 will be equal to S31. Okay. Now, as I said, even though all the ports of S of the T cannot be matched, one of the ports can. So we shall assume that port 2 is matched, and therefore S22 is equal to 0. Similarly, here also S22 is equal to 0. Fine. And also from symmetry, we can, one more property we can write is that because 1 and 3 are symmetric, ports 1 and 3 are symmetric, therefore S11 is equal to S33. Similarly, here also S11 is equal to S33. Okay, so now with these properties established, I can write my S parameter matrix. First, let us analyze the E-plane T. So my S parameter matrix for the E-plane T, I can write it like this. this comes, it is minus 1 S23 is equal to minus S12. This comes from this equation. Okay, now since the device is lossless, let us apply the unitary condition. So applying this condition on this matrix, we get the following equations. Okay, then we also get S12. So this is row 1 into column 1. This I get from row 2 into column 2. Okay, if I had multiplied row 3 with column 3, I would get this same equation. Okay, so now let me multiply, let's see, row 1 into column uh, column 2. So if I multiply row 1 into column 2, then what do I get? S11 S12 conjugate, okay, minus S13 S12 conjugate is equal to 0. Okay, and if I multiply row 1 into column 3, what do I get? Okay, so from this equation, this one, we call this, let me label this equation. Okay, I call this equation 1, equation 2, equation 3, equation 4. From equation 2, we get S12 is equal to 1 upon square root of 2. From equation 3, we get S11 is equal to S13, and from equation 1, this one, we get so So if we substitute this value in equation 1 and also substitute this value in equation 1, what do we get? We get S11 square plus 1 upon 2 plus S11 square is equal to 1. So from here we have 2 of S11 square is equal to half. So this implies S11 magnitude is equal to 1 upon 2. Okay, so this is the value of the amplitude of the S11 parameter. So then once we know S11 magnitude, we also know what is S13 magnitude, right? And we also know what is S12 magnitude. So with this now we can form our S parameter matrix, which will be like this: S11, S12, S13, S12, 0, and then this will be like this. And 1 upon square root of 2 e raised to j theta 1 2 half So we know the amplitudes, but we don't know the various phases like theta 1 1, like theta 1 1, theta 1 2. So we have to find out only two phase terms, theta 1 1 and theta 1 2. We know all the amplitude values. So the question is, how do we find out these amplitude values? Now let us go back to our T, structure of T. So you see that, recall that I had said that if you extend the length of a transmission line, you don't change the characteristic impedance, but you change the phase. So if I change the lengths of this terminal 1 and terminal 2 and terminal 3, I beg your pardon, because both are symmetric, so that this theta 1 1 term becomes equal to 2n pi, where n is some integer. Then this phase term, this theta 1 1, will vanish. Similarly, if I change the length of this terminal, this port 2, change it, either increase or decrease it, so that again my theta 1, 2 becomes equal to 2m pi, where m is an integer. Then also I can make this theta 1, 2 terms vanish. And that is what I will do. And after doing that, see here you might say, why am I changing the length? How does the phase of the S parameter depend on the lengths of these t's? The reason it depends is because any extra phase that appears in the S parameter can be corrected by making the wave run an extra length, so that we are forcing the phase change to be 2n pi, okay, or 2m pi. So that is possible. So after doing that adjustment, what we get is that the S parameter matrix becomes something like this. So this is the S parameter matrix of a E-plane T. Now I leave it as an assignment for you to find out how to derive the expression for the S parameter matrix of this H-plane T. The only difference, as I said, between the H-plane T and the E-plane T is this relationship. If this relationship, there is no negative sign here, and as a result, you will see that this will become plus for a H-plane T. Other than that, the S parameter matrix remains the same. Now, let us take an example, a very interesting example about a T, and try to establish why losslessness, reciprocity, and matching at all ports cannot go together. So let us consider a simple T. Okay. So let's say that the voltage between these 2 points is V0. So the power input, if I want to find out what is the power input here, and say we assume that the impedance seen from this end is Z1. So then this becomes a matched load. So this Z1 transmission line having characteristic impedance Z1. By the way, Z1, Z2, and Z3 are the characteristic impedances of the 3 transmission lines. Okay? Z1 is the characteristic impedance of this transmission line, Z2 is the characteristic impedance of this transmission line, and Z3 is the characteristic impedance of this transmission line. Between these 2 terminals, the impedance load seen is Z1. Therefore, can I say that P in is simply equal to V0 square upon Z1. V0 is the RMS voltage. Okay. So that is the P in, because this whole system is lossless. So the power flowing in this direction is given by this value. And that's why, and since the system is lossless, so the power flowing at this point is also equal to the power flowing at this point. So P in is equal to V0 square by Z0. Now, what is the power flowing in this transmission line and this transmission line? Can I say, suppose I call the power flowing in this transmission line P2 and this transmission line as P3, then can I say P2 is equal to V0 square upon Z2 and P3 is equal to V0 square upon Z3. The reason being that, assuming that this transmission line, this one, is matched, okay, by a load Z2 at this end, and this transmission line is matched by a load Z3 at this end, the total impedance, input impedance seen for this transmission line from this point is Z2, and so the total power flowing for this transmission line is V0 square upon Z2. Similarly, the total power flowing for this transmission line is V0 square upon Z3. Now here Z1, Z2 and Z3 are the characteristic impedances and they are real. Now since the system is lossless, we can write P in is equal to P2 plus P3, and so from here we can write 1 upon Z1 is equal to 1 upon Z2 plus 1 upon Z3. In other words, Z1 is equal to the parallel combination of Z2 and Z3, and that's why we can achieve matching at port 1. At this port we can achieve matching because we can adjust Z2 and Z3 so that the parallel combination becomes equal to Z1. For example, if Z2 is equal to Z3, then we know that Z1 will be simply equal to Z2 upon 2, right? But can we also achieve matching at these ports? So to achieve that, say we want to achieve matching at port 3, we need to have Z3 equal to the parallel combination of Z2 and Z1. But we know that Z1 is already equal to, is given by this equation, which would mean that Z3 will be equal to Z2 parallel to Z2 upon 2. But we also know that Z3 is equal to Z2, and so this equation is not possible. So you see, if I have to have all the input power flowing to the output ports without any loss, then this fallacy will arise that I can have only one port matched but not the others. And that's why, in order to match all the ports, I need to, if I could have done the matching had I been given the freedom to lose some power. If I lost some power, then this equation need not be always valid. And then I can selectively adjust my Z1, Z2 and Z3 to get matching. And the reason for showing you this example is this will give you an essence as to why, if we have lossless system and reciprocal system, then matching is not possible at all ports. Okay. So with that, we come to the next type of 3-port network, which is called a circulator. A circulator is the first circuit that we will be studying, which is non-reciprocal. So coming to circulators, which are 3-port devices, but they are not reciprocal. They are matched at all ports. And lossless. So let us try to analyze the S parameters. So the S parameter matrix will be something like this. Now, since they are lossless, the unitary condition will hold. So let us try to evaluate the unitary condition. So now from this we get the following equations.